Good morning. My name is Erol Sancaktar. This morning, I would like to talk about Excimer laser treatment of nylon fibers for improved adhesion to vulcanized natural rubber. I would like to acknowledge my co-worker, Professor Satilmis Basan, at Chemical Engineering Department of Hittat University in Turkey. Physical and chemical changes with UV excimer laser in polyamides or nylons have been investigated in the past. The surface of the polyamide fiber generally requires periodic shape modulation by UV excimer laser. The size of the roughness created by the UV excimer laser varies from a pattern similar to a wave of several microns to higher depths. We make a conjecture that such laser-induced structures on fibers providing higher surface roughness may improve fibers' adhesion to rubber compound. The gaps between these roll-like structures provide more approachable space for the relatively soft matrix. Thus, additional gripping force applied on fibers from rubber contributes to the adhesion of fibers to the matrix. A theoretical prediction of increase in bonding strength of nylon fiber rubber composites could be acceptable if showing a reasonable agreement with fiber pull-out test results. We had the following goals for our study. We wanted to improve adhesion between nylon fibers and natural rubber without the use of adhesives or chemical etch methods. We wanted to apply various UV laser treatments on the surfaces of nylon fiber in order to increase bonding strength of fiber natural rubber composites by inducing topographic features. With these types of topographic features, we are talking about features similar to the picture that I show on the upper right, which depicts an excimer laser irradiated titanium surface that we worked on in the past. You can see here that even titanium can be irradiated and melted on the surface to obtain such topographic wavy patterns. We then wanted to observe the induced surface modifications by microscopy and perform pull-out adhesion strength tests using the method developed by our research group for determining bonding strength of nylon cord fibers to natural rubber. Earlier studies on physical and chemical changes on polyamide surfaces due to UV excimer laser irradiation showed that the surface of polyamide fiber generally acquires periodic shape modulation by UV excimer laser. The size of the roughness created by the UV excimer laser varies from a pattern similar to a wave of several microns to higher depths. In the past, we used a 248 nanometer wavelength krypton fluoride excimer laser to ablate aluminum and titanium substrates, which were subsequently bonded with an epoxy adhesive. We used 20 to 1000 pulses with 250 millijoule fluents. The ultimate strength of the irradiated aluminum substrate joints were 15% greater than the controls, and the strain at fracture for the irradiated joints were around 60% greater than controls. With titanium, we did not observe a significant effect for failure stress or strains, perhaps due to the strength and hardness of titanium substrates for the ablation conditions irradiation conditions we applied. However, when we bonded the samples, the elastic modulus changed from 51.7 for the control to 30.7 megapascal with irradiation using 20 pulses, showing a softening of the interface of the bonded joint. We also performed nonlinear viscoelastic modeling by using numerical analysis of the fiber matrix interface in composite materials. We showed that increases in interface thickness reduces fiber end stress concentrations when in composite form with a polymer matrix. We also showed that the interface modulus also affects the stress state, with typically softer interfaces acting to reduce the stress concentrations. We prepared the rubber compound, which was filled with carbon black in natural rubber, in internal mixers by starting with an unvulcanized form of the natural rubber, which had the commercial designation SMR-CV60. Such internal mixers are quite practical. They have good control of weight loss and short mixing time. So we compounded the carbon black with the natural rubber containing the vulcanizing agent, and we compounded them using 0.3 revolutions per second at room temperature for 20 minutes. We then press cured these partially to 2 millimeter thick sheets, which were eventually laid in molds to make the pull-out test specimens. The conditions used were 28 megapascal pressure at 100 degrees centigrade over a 35-minute period. The compound formula is shown on the slide on the right-hand side table, and the cords were supplied by Triangle Tire Company of China. The irradiation, as I mentioned, was done by using an Excimer laser by Lambda Physics. The samples were irradiated in under nitrogen stream in groups of 6 cords at a time. Repetition rate was 1 Hertz. The applied energy density per laser pulse and the number of pulses were 200 millijoule per square centimeter and 200 to 500 pulses. We also use an optical microscope to observe this. The pull-out test we used was similar to the STM D4776H test, but we designed and manufactured our own mold in-house, which is shown on the lower right. The cavities are used to lay down the layers of the partially vulcanized rubber sheets, in between which the nylon cores are sandwiched. The embedded length is induced on one of the sections of the mold, one of the cavities, and the other side contains a full length of the fiber, which when closed and cured produces the sample shown on the upper right. And then this sample is then gripped in a tensile test machine and pulled to obtain the pull-out force and shear strength. This is obtained by performing the equilibrium condition described by the equation at the bottom of the slide. The shear stress is tau, which is the adhesion strength. The stress in the fiber is sigma. This is obtained under the pull-out force F, shown on the left. The embedded length is L sub E, and the fiber radius is R. The surface conditions, as seen by optical microscopy, are depicted on the upper left under different numbers of pulses. The waviness and ripple structure increases with the number of pulses. And typical pull-out load versus extension curve is shown on the lower left. This was obtained by using 200 pulses with fluence of 200 millijoule per second. The variation of pull-out load and maximum adhesion are shown on the right as functions of pulses. The upper graph shows that the pull-out load increases monotonically until 300 pulses and then levels off. It becomes approximately constant. The lower of the curves show the variation of maximum adhesion with pulses. Again, the maximum adhesion increases monotonically up to 300 pulses after which an approximately level adhesion force is obtained. So in conclusion, we can say that the results of our study suggest that excimer laser irradiation method is an effective method in improving the adhesion of nylon cord to tire rubber. Laser-induced region on nylon fiber surface reveals typical wavy structure. This observation reveals nylon cord has high absorption coefficients for laser light at 248 nanometer, which tends to develop distinct laser structure. The surface structure depth for nylon cord is governed by the number of laser pulses. Increasing the number of laser pulses increases the structure depth. Ablation at low number of pulses creates shallow and irregular structures which merge together upon further ablation, and the mean distance between the features enlarges, resulting in a more coarse structure. As revealed by the pull-out test, the natural rubber nylon composites on these composites, excimer laser irradiation results in an incremental increase of adhesion strength to natural rubber compound when comparing to untreated cords. A continuous increase in adhesion strength is observed with increasing number of laser pulses up to 300 pulses. We attribute this behavior mostly to improved mechanical adhesion within the wavy structure regions on cord surfaces. Thank you very much for your attention.